Welcome to Chapter 4, where we explore how supercritical fluid technology has moved from laboratory curiosity to industrial workhorse. Today, supercritical fluids power multi-billion-dollar industries worldwide. From the extraction processes that produce your decaffeinated coffee and craft beer hops, to chromatography systems separating pharmaceutical compounds, power cycles promising revolutionary efficiency, and materials processing creating aerogels and nanoparticles. This chapter reveals why supercritical fluids represent one of the most important green chemistry technologies of the 21st century. Supercritical fluid extraction, or SFE, exploits the unique solvent properties of supercritical fluids. The process operates in three distinct phases. In the extraction phase, supercritical CO2 flows through raw material, dissolving target compounds. In the separation phase, the extract-laden CO2 enters a separator where pressure drops, causing CO2 to become a gas and release dissolved compounds. In the recovery phase, pure extract is collected, while CO2 gas is recompressed and recycled. Key advantages include zero solvent residue, low temperature operation, preserving heat-sensitive compounds, tunable selectivity through pressure and temperature control, and FDA GRAS status for food and pharmaceutical applications. Coffee decaffeination was one of the first large-scale industrial applications of SFE, pioneered in the 1970s and 80s. The process begins by moistening green coffee beans to about 30 to 50% water content. Supercritical CO2, at around 80 degrees and 20 megapascals, selectively extracts caffeine. The caffeine-laden CO2 passes through a water scrubber, where caffeine transfers to the water phase for recovery. Clean CO2 recycles back to extraction. Cycles take 8 to 12 hours, but achieve greater than 97% caffeine removal. Modern plants process 50 to 100,000 tons annually. Major coffee producers like Nestle and Starbucks use this technology for their premium decaf products. The brewing industry uses SFE extensively for hop extraction. Hops contain alpha acids that provide bitterness, essential oils that contribute aroma, and flavonoids for flavor complexity. Different extraction conditions target different compounds. At lower pressures of 8 to 10 megapascals and 40 to 50 degrees, you extract hop oils with aroma, but without bitterness. At higher pressures of 20 to 30 megapascals, you capture alpha acids for consistent bitterness. The extracts offer advantages over whole hops: consistent bittering values, extended shelf life, reduced shipping weight, and year-round availability regardless of harvest timing. The global hop extract market exceeds $500 million annually. The rapidly growing cannabis industry has made supercritical CO2 extraction the gold standard for cannabinoid processing. The process typically involves multiple stages. Subcritical extraction at cold temperatures removes waxes and lipids. Supercritical extraction at 35 to 50 degrees and 15 to 30 megapascals captures cannabinoids like CBD and THC. Lower pressure stages can preserve delicate terpenes for full-spectrum products. This approach produces CBD isolates with greater than 99% purity, full-spectrum extracts containing multiple cannabinoids and terpenes, and broad-spectrum products with THC removed. The extraction service market alone exceeds $2 billion annually, with the legal industry driving significant innovation. Supercritical fluid chromatography, or SFC, represents a hybrid between gas chromatography and HPLC, combining the best of both. The speed advantage is dramatic. SFC analyses typically complete in 3 to 10 minutes versus 15 to 60 minutes for equivalent HPLC separations. This speed comes from the physical properties of supercritical CO2. Lower viscosity enables higher flow rates without excessive backpressure, and higher diffusivity improves mass transfer, producing sharper peaks. Environmental benefits are equally impressive. SFC uses 80 to 90% less organic solvent than HPLC, dramatically reducing waste disposal costs and environmental impact. Supercritical Co-2 is emerging as a revolutionary working fluid for power generation cycles. The SCO2 Brayton cycle achieves 48 to 52% thermal efficiency at turbine inlet temperatures of 500 to 700 degrees, matching or exceeding conventional steam cycles at lower temperatures. Turbomachinery is remarkably compact, about 1/10 the size of equivalent steam turbines, because of CO2's high density near the critical point. The cycle is compatible with dry cooling, eliminating water consumption. The U.S. Department of Energy is funding demonstration projects targeting over 50% efficiency. Applications include next-generation nuclear reactors, concentrated solar power plants, and industrial waste heat recovery. Aerogels are among the lightest solid materials known, and supercritical drying is essential for their production. The challenge is that wet gels have delicate nanoporous structures with pores just 2 to 50 nanometers across. Conventional drying creates liquid-gas interfaces with high surface tension, and the resulting capillary forces collapse the pore structure. The solution is supercritical drying. By exchanging the pore liquid with supercritical Co-2, then slowly reducing pressure, you avoid ever creating a liquid-gas interface. Above the critical point, there's no surface tension, no capillary stress, and the aerogel structure is preserved. The resulting materials have densities as low as 1 milligram per cubic centimeter, porosities up to 99.8%, and exceptional thermal insulation properties. Supercritical fluids enable several methods for producing nanoparticles with controlled properties. RESS, or rapid expansion of supercritical solutions, dissolves a compound in supercritical Co-2, then rapidly expands it through a nozzle. The sudden loss of solvent power causes instantaneous precipitation of very fine particles, typically 0.1 to 10 micrometers. SAS, or supercritical antisolvent, sprays a solution into supercritical Co-2, which extracts the solvent and causes the solute to precipitate as nanoparticles. PGSS, particles from gas-saturated solutions, atomizes Co-2 saturated melts, with Co-2 expansion providing both atomization and cooling. Each method suits different applications and compound types. Let's summarize the industrial landscape. The pharmaceutical segment leads with $1.2 billion, driven by API extraction, chiral SFC, and particle engineering. Food and beverage represents $800 million, primarily coffee decaffeination, hop extraction, and essential oils. The cannabis industry has grown to $2.5 billion. Energy applications for SCO2 power cycles are projected to exceed $500 million by 2030. Materials processing for aerogels and nanoparticles accounts for $400 million. Environmental applications, including SCWO, represent $300 million, but are the fastest-growing segment. Overall, the supercritical fluid chemicals market is growing from $2.9 billion in 2024 to a projected $7.9 billion by 2034. Next, we'll explore advanced topics and future directions.